So greetings to you all and welcome to our Zoom-based seminar. My name is Professor Ann Karagosian, and it is my privilege as the director of the Promise Armenian Institute at UCLA, as well as being a faculty member in UCLA's Department of Mechanical and Aerospace Engineering, to welcome you to the latest in our series of talks presented by our current PAI postdoctoral scholars. So today we are delighted to welcome Dr. Ashley Kuzanyan, a 2021-22 Promise Armenian Institute postdoctoral scholar who is working in the UCLA MAE department. And she will offer a seminar, which is what we call them in engineering and science, not a lecture, entitled Doing Science in Armenia from a Personal Outlook to Nanoscale Thermoelectric Photodetectors. This special seminar will not only present Dr. Kuzanyan's UCLA-based research pertaining to nanoscale thermoelectric photodetectors, but will also focus on current trends in science and engineering in the Republic of Armenia and the nature of pursuing a career in science in this rapidly developing country in the South Caucasus. Astley's talk is also somewhat of a first for our UCLA Promise Armenian Institute in that it is a science and technology focused talk rather than with an emphasis in the social sciences or humanities or arts, which have heretofore been the foci of our Promise Armenian Institute programming. We are also delighted to acknowledge the co-sponsorship of this event, not only by our UCLA MAE department, but also in another first by the National Academy of Sciences of the Republic of Armenia. And hence we are having a relatively early start time of offering of the seminar in Los Angeles to enable viewers from the Republic of Armenia to watch without too much of a time difference challenge. And on behalf of the Promise Armenian Institute and UCLA, I would like to acknowledge our presence on the traditional, ancestral, and unceded territory of the Gabrielino Tongva peoples. So I will provide a formal introduction for our speaker in a moment, but just let me know, for those of you watching live via the Zoom seminar platform, you do have an opportunity to ask questions either during, but preferably after the seminar, and pose them either by speaking out loud orally or typing a question in the chat window. And please, of course, be sure to be as specific and succinct as possible in your question. Please note as well that this event is being recorded for future viewing at our Promise Armenian Institute website and potentially on our YouTube channel. And in the unlikely event that this Zoom seminar will drop for any reason, please just connect right back to the same link you used to get in, and it will put you back in our Zoom session. So now it gives me great pleasure to introduce today's speaker, Dr. Ashley Kuzanyan. Dr. Kuzanyan, as I mentioned, is a UCLA Promise Armenian Institute postdoctoral scholar during the current academic year, working in the Department of Mechanical and Aerospace Engineering with Professor Artur Davoyan. Ashley received her PhD in laser physics from the Supreme Certificate Committee of the Republic of Armenia. She received her MS degree in radio engineering and telecommunications from the National Academy of Sciences of the Republic of Armenia International Scientific Education Center, and she received her BS degree in radio physics from Yerevan State University. Astghik's research at UCLA focuses on single photon detection. She also holds an appointment as a researcher at the Institute for Physical Research of the National Academy of Sciences of Armenia. So Astghik, I will now turn this seminar over to you.
Dear Anne, thanks for the introduction. Give me a moment. I will share my screen. Okay, as I said, today I will talk about Armenia, where I come from.
You want to bring up the camera, I think, also.
I don't know why, but I cannot turn on the camera.
Sure, it's all right.
Okay, I'm sorry. I will talk about Armenia, where I come from, and about my research topic, thermoelectric photodetectors, which I start in Armenia and continue at UCLA. Armenia is located in the Middle East. It is a small and developing country and has no access to the sea. Armenia has rich and beautiful nature, lots of mountains, canyons, mountain rivers with waterfalls, and beautiful lakes. One of the symbols of my country is Ararat Mountain. According to the Bible, Noah's Ark landed to Mount Ararat after the flood. Armenia is an old country and has lots of historical monuments, one of which is Garni pre-Christian temple in a Greek style. Also, Armenia is the first country to adopt Christianity as a state religion, so we have lots of old churches. Armenian science history goes back several thousand years. In Armenia, we have a prehistorical architectural monument like Stonehenge, Karahunj Observatory. And I can say that Karahunj is older than Stonehenge by about 3,000 years. As I told before, Armenia is a mountain country and nature gives a big opportunity to work in cosmology and astronomy.
You know what, I'm gonna have to discuss this with my son because he was the one who wanted it, so let's see.
Could I ask that everybody mute themselves? We are in a seminar format rather than a webinar, so we can hear others if you are not muted. Thank you.
In the highest mountain in Armenia, Ararat, is located three important scientific objects: Cosmic Ray Station in 3,200 meters, Burakan Observatory, and Orgov Radio Optical Telescope. Today, science in Armenia is driven by the National Academy of Science. Priorities in the Department of Physics are astronomy and astrophysics, high energy physics and cosmology, optics and laser physics, as well radio physics and engineering. For the development of all of this and science in general, we need smart and young scientists. Good education is the first and most important start point. Armenia is a small country, and the Armenian students' body is comparable to UCLA. Since Armenia is a developing country, science funding from the government is not high. For 2022, it is about $50 million US. For the comparison with other countries, I present science funding from the government in the percent of GDP. In Armenia, it is about 0.25%, which is much lower than world average. And I was a little bit surprised that the highest percent of GDP, which is going for funding of research, is in the small country Israel. But India, Armenia is 0.12% of total population work in science. At the same time, in Armenia, researchers' salary comes from the government is comparable with average salary in Armenia, which is about $410 US. Researcher salary become much higher with research grant funding. But we have good news. Next year, science funding from the government will be increased in 70%. And this year, Science Committee has introduced 2 new grants for funding new research labs or groups under supervising professors from abroad. This grant's aim is to attract scientists from the diaspora and improve international collaborations. The first one is for moving to Armenia, found a lab there and work at least 5 years. The second one is for remote supervising of the group in Armenia. Armenian government also has target grants for supporting PhD students, young scientists, and women in science, which is important for me. I am from the Institute for Physical Research. Institute is located in small town Astghik and has a great campus, which called Gitavan, which means science town. Beside the office and lab buildings, it has an apartment for their employees and families, a kindergarten, a tennis and football court, and a big apricot garden in front of the lab buildings. My family also work in this institute. So I grew up in this campus, went into this kindergarten, live here, play in this garden and in the institute labs from my childhood. And I can say that I have been institute for more than my whole life. In the institute, we have 4 general topics for research: theoretical physics and quantum information, optics and laser physics, solid-state physics and crystal growth, material science and engineering. I'm working in the material science laboratory. As one of the basic research fields in our institute is optics and laser physics, every year in our institute we organize international conference laser physics, as well international school frontiers in optics and photonics, and international symposium optics and its applications. As astronomy, cosmology, and laser physics are popular research areas in Armenia, and we have a good knowledge of material science, we can develop low radiation and single photon photodetectors to apply it in these areas. Single photon detectors have many other applications too, particularly quantum computing and cryptography, medical imaging, telecommunication systems, etc. Photodetectors are light or other electromagnetic radiation sensors. Single photon detectors are the most sensitive photodetectors, which can register the lowest radiation, just 1 photon. After electromagnetic radiation absorbed, some processes go on the detector and in the result generated signal. This signal shows the fact of photon absorption and gives some information about radiation, such as wavelength and intensity. There are many types of photodetectors, but how we can compare the detectors or what we want from a good detector. To get a large signal, we need to detect photons as much as possible. Ideally, detect all photons which drop on the detector. So we need high quantum detection efficiency at the wavelength of interest. Noises is another problem with detectors. They come from inside of detector like thermal noises and outside like amplifier noises. To register low signal coming from photons, we need to have low noise level. The other most important parameter of the detector is recovering time. Short recovering time makes it possible to register more photons over a period of time. So we need a detector with a short recovering time, which means with a high count rate. Nowadays, most popular detectors are avalanche detectors, such as photomultiplier tubes and semiconductor avalanche photodiodes. The work principle of this detector is similar. After photon absorption, electrons are ejected from the surface and the result of photoelectric effect. Then electrons are multiplied by the process of secondary emission. For a semiconductor avalanche diode goes on the same process for the electron-hole pairs. These detectors have a great advantage. They can work at room temperature, but they also have disadvantages like low count rate and high dark count rate. Another type of detector are superconducting detectors. Today, superconducting nanowire single photon detectors have the best characteristics. These detectors work on the critical point of the superconductivity transition. After photon absorption, the pair Coopers broke and form a localized non-superconducting region or hotspot where the resistance is increasing and it creates measurable voltage pulse. In a short time, the detector is recovered and can register the next photon. But these detectors have some disadvantages, such as low working temperature and strict working requirements. Now we can compare these detectors' parameters. Photomultiplier tubes and avalanche photodiodes work in about 200 Kelvin temperature. Superconducting nanowire single photon detectors work in much lower temperature, in about 2 kelvins. But at the same time, they have high detection efficiency, about 98%, low dark count rate, 10 Hertz, and count rate about 3000 megahertz. So I have a question. Can we make a detector that is efficient but works at a higher temperature? We think that thermoelectric photodetector can achieve that. Thermoelectrics are the semiconductor materials which has an interesting phenomenon called Zebic Effect. The Zebic Effect is a direct conversion of temperature difference to electric voltage. That voltage can calculate by this equation, where delta T is the temperature difference in the thermoelectric material. S is the Zebic coefficient. Zebic coefficient is the thermoelectric voltage in response to the temperature difference across the material. There are some photodetectors based on thermoelectric materials which works in higher temperature. These detectors are very fast because of nanoscale sizes. I'm sorry. And broadband because don't depend on the band gap. We consider thermoelectric photodetectors with these designs. Thermoelectric detector detection pixel has an absorber, thermoelectric sensor, and heat sink. Then we consider different materials for each part of thermoelectric detector. Operating circle of thermoelectric photodetector is like this. After photon absorption, in the absorber form the hot spot, and in the result of heat distribution processes, temperature in absorber is increasing. In the thermoelectric sensor, generated temperature difference, and as a result of Zebic effect, generated voltage. After heat distributed in the sensor, then in the heat sink, and temperature difference decreasing and voltage come down. After heat goes to the substrate, detector recovered and ready to register next photon. Based on this design, scientists from Naval Research Laboratory at UCLA made the prototype of detector with antimony absorber and heat sink, and gold and iron thermoelectric sensor with superconducting contacts. Here you can see detector response to the laser pulse. We can see that the signal is increasing in a short time after laser pulse, achieve the maximum, then drop to the noise level. This time shows the detector count rate. Before starting single photon detection hard experiment, we need to study lots of characteristics of the detector and their dependence from the detector size and materials. We study heat distribution processes by computer modeling using the finite difference method. As a result of simulation, we get the dependence of temperature on time for each part of the detection pixel. We can see that after photon absorption, the temperature is increasing, achieve the maximum, then comes down. In this curve, we consider the maximum temperature, time to achieve that maximum, and the recovering time, which is the time in which the signal fall down to the background value, which we considered 0.1 millikelvin. As multiplying the temperature maximum and thermoelectric material Zebic coefficient, we can calculate the voltage which can generate it in the thermoelectric. And the detector count rate, which will be inverse value of the recovering time. Next, we study thermoelectric characteristics dependence from the detector size, and we modeling how will be voltage maximum and count rate dependence from the sensor thicknesses. We can see that count rate achieve about 50 gigahertz when the sensor thickness is increasing from 4 to 0.0 from 0.1 micrometer. But at the same time, voltage is little bit decreasing because in thin thermoelectric sensor cannot generate a high temperature difference. I said before that these detectors are broadband, and it is important to determine the energy of absorbed photon. So we study maximum voltage and count rate dependence from the photon energy. In these curves, we can see that the voltage dependence from the electron energy is linear and increase together. It is very important because measuring the voltage, we can calculate the photon energy. But at the same time, count rate is decreasing when photon energy is increasing. Because after photon absorption, in the detector are much heat and detector need more time for recovery. For many applications of single photon detectors, it is important not just detect the photon, but also to have a chance to count the photon number. So I study what will be happen with the signal of thermoelectric photodetector when detector will absorb more than one photon at the same time. For example, 3 photons. In the graph, we can see 3 similar peaks under the points where photons absorbed. This peak's value is the same in the same detection pixel absorbed 1 or 2 photons. So this cannot give much information for count the photons, but the recovering time when absorbed 3 photons is much higher. So when we know maximum voltage and recovering time together, we can calculate photon counts. Based on all of this result, we decided to fabricate thermoelectric detection pixel heterostructure. Here I present tungsten, cerium hexaboride, tungsten, 3 different heterostructures, which we made by electron beam deposition method. These 2 samples deposit in aluminum oxide substrate. The second one is in tungsten substrate. We study these heterostructures' electrical and optical characteristics. As I said before, signal to noise ratio is one of the most important characteristics of the detectors. Noise often presented by the noise equivalent power, which is expressed the minimum detectable power per square root bandwidth of a given detector. In other words, it's a measure of the weakest optical signal that can be detected. Usually, noise equivalent power is obtained by measuring detector gain and voltage noise depends voltage noise density at the output and can calculate by this equation. So when we have a real detector, inside of detector we have lots of electrons and phonons, which fluctuation made some noises like thermal noises. But detector has lots of other noises too. So when we have a real detector, we can measure that noise's voltage. And after photon absorption, we can measure detector gain and calculate noise equivalent power. For our detector, noise equivalent power is given by Johnson and thermal noises. And in the equation, we can see that noise equivalent power in total is dependent on detector size, detector working temperature, resistivity, heat capacity, and Zebic coefficient. Here I present noise equivalent power dependence from thermal conductivity and Zebic coefficient. And we can see how high Zebic coefficient and the low thermal conductivity made the noise equivalent power smaller. So noise equivalent power can be smaller than 10 to minus 12 for the structure with materials that have thermal conductivity smaller than 100 and Zebic coefficient higher than 115. Iron and antimony too are the best, but cerium hexaboride and lanthanum cerium hexaboride is not bad too. But we need to study the dependence from resistivity too. Here I present noise equivalent power dependence from the thermal conductivity and resistivity in 75 Kelvin temperature. And we can see that to have a low noise equivalent power, we can use the material which have low resistivity too. So noise equivalent power can be smaller than 10 minus 12 for structure with used the material which resistivity is smaller than 10 minus 7. Iron antimony too has big resistivity, so it cannot work. But cerium hexaboride and lanthanum cerium hexaboride are good and can be used as a thermoelectric sensor. As an absorber, we can use niobium and lead. I have shown that thermoelectric photodetectors has high count rate. Also, they can determine photon energy. Thermoelectric photodetector can count photons, and noise equivalent power at 75 Kelvin is about 10 minus 12. So I can insist that thermoelectric photodetectors can be real competitors to other detectors. I will continue my research, and our next step is this. At first, we need to design and modeling of the detection pixel, then fabricate prototype sample of the detector and study their optoelectronic parameters. I am thankful to Promise Armenian Institute at UCLA, UCLA Mechanical and Aerospace Engineering Department, National Academy of Science of Armenia, and the Institute for Physical Research of National Academy of Science of Armenia for supporting this talk. And special thanks to Promise Armenian Institute at UCLA for funding my research at UCLA. Thank you.
Wonderful. Thank you so much, Astghik, for this really very interesting summary of your research, as well as the background on the current state of science in Armenia, as well as the history of Armenia itself. So that was really fascinating. Our floor is now open to questions. So once again, this is an unusual format for our Promise Armenian Institute, where we usually don't see who everyone is who's in attendance, but this is the format that we use in our department, the seminar format. Is there anyone who would like to ask a question of Astghik? You can either, you could actually use the raise hand function. You can, if you're not comfortable speaking, or if you're not able to with the device you're using, you can type a question in the chat. Any questions from our audience?
Yes, I'd like to ask a question.
Thank you.
In the case of 3 photons, you had multiple peaks. The second and third peaks, are they harmonics, or what are those peaks? And also, what is the detection time that you have been able to measure, the smallest detection time?
The detection time depends from the detector size, of course, and the materials. Usually it's about from picosecond to nanosecond. That 3 peaks, it's not harmonic. It's in 3, here is the absorber surface, and photons similarly as in the same time absorb in 3 different points. And that peaks are from each photon, and that measured under the point when they absorbed. And the value of that peaks are similar, and that value is similar when absorbed 1 or 2 photons in the same detection pixel too. So we can count the photons when we know the recovering time too, because when there are not 1, 2, 3 photons, the recovering time is increasing, and depends from the photons number. How much photons absorbed, the recovering time is increasing.
Yes, but I noticed that for each photon, there are multiple peaks. That's what I'm asking about.
Yeah, because that is, I will try to share my screen. Here, these multiple peaks are spatiotemporal dependence of the temperature, and the smaller peaks are the temperature in other parts of detector. It depends from the density from the absorbed points, from a distance from the absorbed points.
Okay.
Thank you.
I have a quick question. So you gave a great breakdown on the total budget and comparison with other countries, and also the salaries. Can you give a brief comment on the amount of funding that typically groups have? Like, what is the grant size, and what is the funding that groups in Armenia have in general?
From Armenian government, in general, before this year, it's about 12 million US dollar per year. It's about 6,000 US dollar, 7,000.
12 million Armenian drums?
Yes, Armenian drums. And but this year it is increasing. Increasing at 3 times, if I know correct, because I was here then it started the project. And the salary from the grants, government grants, is about $300 per month.
For the entire group? Or
No, for each person. Generally, the grant groups is 5 or 7 people.
Mm-hmm.
Because in general there are small grants, but Armenia can apply grants for European grants too, and NATO grants too, but there's ISTC, and the salary there is much higher than from government. But I think our government is in the right way to increasing the salaries and made most important science in Armenia.
Thank you. Clearly, the cost of living is very different in Yerevan from what it is here, almost anywhere in the United States. Maybe I could ask a quick question, Astghik. You talked about some of the next steps in the research, and you've discussed the fabrication of some of these heterostructures, I guess, that were done here at UCLA, is that right? Or was that done elsewhere?
We will start to do it at UCLA, but I'm not sure that we will have enough time to finish everything. But I think after I will go back to Armenia, we will continue our collaboration with Professor Davrian, and we will have great result together.
Great. So the fabrication might continue here, but you would continue the computational work. Is that right?
In Armenia, and then we can try to send the samples to each other and do other measurement processes together and have some results.
Great. Could you just comment briefly, were there any numerical challenges in the computations you did? Did you have any issues with respect to spatial or temporal resolution types of problems, or this was very straightforward to do the computations?
Doing the computation gives lots of information about detection pixel design tool, because at first we think that detection pixel will be in one layer, but computation method shows that when we have absorber, thermoelectric bridge, and heat sink. When photon absorbed in different areas of the absorber, the signal is a difference and depends from the part when a detector is absorbed. But in multi-layer sensor, we don't have that problem. And using the characteristics of the materials, we can calculate count rates, maximum temperature difference and voltage, but in our model we don't compare noise level yet. We will do that in the next step, and dark count rate we don't calculate for this time.
Thank you. And I see we have a question that is posed by Mikhail.
Hi.
Yes.
Thank you very much for a nice presentation. I have a question. So what are the disadvantages of these photodetectors? Is it high cost, like difficulty of fabrication, or what is it?
Disadvantage for this detector for single photon detection can be a temperature. It will be higher than in superconducting detectors, but not at the room temperature, because the noise level will be much higher to register single photon. Low radiation we can detect, and the big disadvantage that this detector is just a model, and we need lots of time to do experiment and see everything it's working and everything is good too.
Okay, thank you. And second question, the free photon detection which you showed, these photons are of the same frequency,
Yes.
or not? It's
Yes. They are in
Question is
STEM.
possible. Is
Sorry?
it possible to do multi-mode detection with your device?
We cannot do photon counting when the photons are in different wavelengths. For photon counting, we need to know photon energy. We can determine photon energy when the photons come one-to-one, but for photon counting, we need to know the photon energies.
Okay, thank you.
Okay, do we have other questions from our audience? Maybe I could ask one more general question, Astghik, about doing science in Armenia. In the United States, typically the fraction of females engaged in scientific work in engineering and the physical sciences is relatively small, ranging maybe between 5% and 20% or something of that sort. Can you comment in Armenia, are there more women proportionately engaged in this kind of research or fewer? Maybe you could offer your perspective on that.
Now in physics and radiophysics, in the students and in the researchers are about 20 to 30% of women. When I was a student and studied at Yerevan State University, in our course, we have just 5% of girls. We have big course and just 5% of girls. But now that number is increasing, and a lot of people now don't surprised when you are a woman and ask you are working in physics. But I have some strange situation in my life when I applied for the visa and embassy of Latvia, and I have an invitation to go there, and they ask, why you work in physics? You are the woman, it's the profession for the men.
Wow.
Now it's much better.
Well, it's a different kind of environment, I think, in many countries, including Armenia, but we're very happy to have hosted you here at UCLA. I'm so glad you could be here and, help us to be connected in this way to the Armenian Academy of Sciences. And we're very hopeful that this project will enable you to continue in your collaborations, not only with Dr. Davoyan, but with others potentially. Are there any other questions from our audience?
Yes, I would like to ask, what is the next step now? What do you intend to do when you go back to Armenia other than manufacture and test? I mean, do you have any plans of like testing other materials or different layers, or what are the plans?
And now the first plan is consider other materials too, like superconducting materials, which have higher superconducting transition temperature, because have superconducting material as absorber give chance to have low noises. And different structure too to have good absorption for the layers, and to decrease the reflection from the absorber.
But are there any materials that you can think of that can work in a normal, regular temperature?
So I'll chime in here. So there are two kind of schools of detectors, and that's, I think, what Astghik tried to show. One of them is this, avalanche-based type of detectors. Of course, there are many more detectors than that, but sort of generally there are two of them. These are relatively cheap. You can buy them. You can do quantum optics experiments with them, and so on. But because the count rate is low, and the reason that the count rate is low, which means that the amount of photons you can detect per second, is because you have this avalanche process that you need to wait till it passes through, and then the detector gets back to its ground state, and then you can do it again. And you can't do it very often. So what happens is that for quantum communications, for example, in quantum computing, and for other applications, you really limit your bandwidth, you limit the amount of time that you can detect these photons. So essentially it becomes kind of, it's interesting for basic research, but it becomes difficult for practical applications with the use of those. Now, superconducting quantum wire, nanowire detectors, they're really great. They're fantastic by all means, and it's really fantastic technology, but you have to cool it to really less than 1-2 Kelvin temperature, which means that it's like extremely large cryofridges that are out there and very expensive. Only few groups can do it. And especially it's very difficult to bring optics into these cryofridges. So it's like it becomes really engineering problem. So if there is a detector that, you know, has somewhat maybe less established characteristics as compared to the superconducting nanowire detectors, but somewhere in between these two, and can operate, say, at liquid nitrogen temperature instead of going to helium and below, then essentially it's a big savings in terms of investment of the capital investment for detector technology, and you know it's just any lab can do it. So the hope is to have these detectors to try to understand what would be the shape and design of these detectors so that we can make them operate at reasonable temperature, which is not room temperature, but not the helium temperature, so somewhere in the middle. And hopefully they can operate somewhere close to single photon level, or maybe at the single photon level. Now that's the question of design. So how thin, so if I make it very small, then the properties of detectors get really better and better. So the question is where and how can I do it, and all of this, right? So that's the goal pretty much.
But what about if you study alloys of different semiconductors to solve some of these problems?
So that you're absolutely right, actually. So that's exactly the reason that Astghik was showing this last plots on a couple of last slides, these color maps, which was pretty much a parametric study. So that was like, you know, let's try to understand. Suppose that I have some device, right? So what would be dimensions of it? What would be the characteristics in terms of resistivity, Zebic coefficient, and all of that? Which kind of materials or groups of materials that I should use so that I can get better performance? So that was your kind of study. And then we see that there's certain materials that are really good ones. And the hope is that now you run into a different problem, which ones you can fabricate, right? So not all of them you can fabricate.
Yeah. But I guess it's a very good research, and I think you're in the right topic, and that's very important for Armenia. And I congratulate you.
Thank you.
I have one more question. When we're speaking about single photon problems, what means broadband? What kind of frequencies means broadband? What kind of frequencies requirement are there for the single photon detectors?
I guess it's Astghik, right?
What frequencies are required for single photon detectors to speak about broadband detectors?
Frequency which have the photon or the detection frequency. It can be different. Our model shows that we can register from infrared to X-ray photons, but with a different absorber. Because the photon which can absorb in the absorber need to have some thickness and characteristics to absorb that energy. For X-ray, it's good for tungsten. For infrared, tungsten is not working. So when we know the energy which we need to absorb, we can consider material which will good for that energy and that frequency.
All right.
Sorry?
Okay. Any other questions for our speaker? Okay, well, let us virtually thank our speaker for a very interesting presentation. And thanks as well to Professor Artur Davoyan for his oversight of the project and his contributions. And of course, I must gratefully thank Asmik Bagdasaryan, whom you actually see here in our seminar, in contrast to our usual webinar, who is our Deputy Director for the Promise Armenian Institute and who has been involved in all aspects of coordinating this event and virtually all other events. So let me just close by announcing there are a few upcoming events remaining during the month of May that are sponsored or co-sponsored by the Promise Armenian Institute. In fact, this evening, Friday, May 20 at 6 p.m., we are partnering with the UCLA Nanoscale Chair and the Department of Near Eastern Languages and Cultures in presenting an in-person event to say with passion, why am I here? This is a book release and a sharing of readings from a compilation of Armenian poetry written by the late Tenny Arlen, who was a UCLA student. So this will be in person at UCLA's Bunch Hall. Tomorrow evening at 5 p.m. at the Astghik Museum, we will be co-sponsoring a presentation by Professor Richard Hovhannisyan, Professor Emeritus of Armenian History at UCLA, who will give a lecture on his recently released book, Armenian Communities of Persia, Iran, History, Trade, and Culture. This also will be live streamed, in fact, on Facebook and YouTube. And then finally, on Tuesday, May 31 at 10 a.m., the UCLA Armenian Music Program will present a day of Armenian music at UCLA in person at UCLA Schoenberg Hall, featuring concerts, educational workshops, and lectures with renowned musical artists. So once again, please visit our UCLA Promise Armenian Institute website or visit us on social media to learn more about these events and future events. So once again, thank you to Astghik, thank you to Artur and Hasmik, and all of you for participating in this event. And we look forward to having you participate in our future events for the Promise Armenian Institute at UCLA. And Hasmik has helpfully posted a link to our website in the chat. So once again, thanks to all of you, and we wish you a good rest of the day or evening.